I would like to thank the organizers for the opportunity to give the first talk at this conference. It's an honor to give such a talk. And the organizers asked me to give a general talk, which I will, but I cannot do the other thing. I was asked to give a review of recent results because I feel I've fallen behind, and some of you guys are much ahead of me in terms of recent development. So I'll just talk about some general questions according to my quirky interests. And those questions are largely motivated by our papers with Josephine SYK. You can find them in that reference list that Mukund distributed this morning. One paper about the soft mode and its gravity dual, and that paper contains a general theory of the SYK model, systematic derivation of various things, and also it addresses some question of the gravity dual, which will be important for the first part of my talk. And the second paper is about quantum 2D black hole, or it's actually called statistical mechanics of a two-dimensional black hole. And it's about quantizing an effective theory, which in this case is the short-chain theory. So these are the two questions I want to address very generally and with hand waving. So the first one is holography. Let me call it partial holography. So there is some evidence that the SYK model is holographic, and it is related to two-dimensional gravity. But if you ask me if it's really holographic, my honest answer would be not quite. And I'll try to elaborate on that, what is missing and how to formulate a sharp condition, and maybe later we can come up with a better model. And question number 2 is how to quantize an effective theory. And we know some effective theories, say in condensed matter, that cannot be reasonably quantized. If we consider the motion of a particle with dissipation in some viscous liquid, then it cannot be quantized consistently as a closed system. The quantum description must include something that provides the dissipation. But in the case of the SYK model, there is an effective theory called the G sigma action that seems self-consistent, at least perturbatively, in 1 over n, and we can try to quantize it. And so far, only its first approximation, the short-chain theory, has been quantized. And that is the subject of our second paper, and there are papers by other people, including Mertens, Verlinde, and there is a group of people working on the subject. So first, let me give a brief introduction to the SYK model, and this introduction is guided by the first question. The original motivation by Sajdiev was different. It was a condensed matter problem to find a system that would be a tractable model of a non-Fermi liquid. And they solved it. It's quite an amazing achievement. It was a long time ago, and they described a used a Hamiltonian that is slightly more difficult to deal with than the SYK Hamiltonian. So just wanted to make things easy, and in particular to remove any symmetry except the conservation of energy. So there will be no symmetry, at least continuous symmetry in this Hamiltonian. So there is a family of Hamiltonians for Q equals 2, 4, 6, and so on. This is the number of interacting fermions, and I'll write the Hamiltonian for Q equals 4. And these chi's are Majorana operators. The commutation relation is usually written with a factor of 2, but I'll use this notation. So there are n Majoranas, n may be chosen an even number, and the Hilbert space can be constructed as a Fock space. We can pair up Majoranas chi to j minus 1 and chi to j, and they can be viewed as a box which can be empty or occupied, and the Fock space will have dimension 2 to the n over 2. And the interactions are random, and this is one trick that condensed matter physicists learned, that it's often easier to deal with random interactions than with some specific interactions. And the average value is 0. Each j is an independent random variable. The tensor is antisymmetric, but otherwise the j's are independent. And they're distributed by the Gaussian law with the second moment, which defines the whole distribution. Capital J is a characteristic energy scale. And in my talk, I'll set j equal to 1. Usually, everything is written in terms of beta j, which is a large number. The interesting regime when it's large, but since j is 1, it's just beta. So beta will be large, and this means conformal regime or nearly conformal. I'll explain what that means. And n is much greater than 1. And one can talk about the balance between n and beta. This is an interesting topic, but let's skip it for now. Sajif and Ye looked at a similar model, and they found the two-point correlation function. They found that in imaginary time, the correlator at 0 temperature has a power law and delta is 1 over q. Since q is 4, it's 1 over 4, but in fact q can be general. This is for beta going to infinity. And later, Parkley and George did the calculation at finite temperature. They guessed, they argued that this system should be conformal and checked that a typical formula that occurs in a CFT works. And that formula is this. One can rescale tau using the variables phi1, phi2, and phi is 2 pi tau over beta. And there will be some normalization, but essentially it's phi 1, 2 to the minus 2 delta where phi 1, 2 is the sine function of phi 1 minus phi 2 over 2. And that looks as conformal dependence because it's just a transformation from the variable tau here to the variable e to the I phi in this equation. Or you can use the tan function if you prefer to work with real variables rather than complex variables. But for me, it's more convenient to use the correspondence between the zero temperature regime and the finite temperature regime using phi going to e to the I phi. So this is one interesting property, and later Sajdev argued that this property is a sign of holography because conformal correlators can be represented as propagators through the bulk. Instead of thinking about this problem, which is really 0 plus 1 dimensional, all these n Majorana modes is just a big blob, and it moves forward in time, and in imaginary time it actually runs around a circle. So this is the circle, and in the middle we can put the Poincare metric for the hyperbolic plane, and instead of considering a correlator between tau 1 and tau 2, or phi 1, phi 2, on the boundary, we can think about propagation of this particle through the bulk. And by the way, if we really use the Poincare metric, then geodesics are circles, parts of circles that are perpendicular to the boundary. So this is a holographic interpretation, but it has too little information. It relies on too little information, and this way many things could be sort of as holographic. I'll show some other signatures of holography later, which are somewhat more convincing, but they're a bit separate from that. Also, Sajdev, Parkley, and George found another amazing property, which is a result of a calculation. It's not a very difficult calculation, but we don't have intuition for that. At least I don't have an intuition for that. The system has an extensive entropy at zero temperature. It's not really zero temperature because when we consider the regime beta then the model is classical or semi-classical. One can use the mean field theory. If beta continues to increase, then the model becomes quantum. But there is one strongly fluctuating mode that can be dealt with analytically. This is also a very interesting fact about this model. Anyway, the contribution to the contribution to the free energy or the entropy due to this mode shows that the entropy continues to decrease as the temperature is lowered, but it decreases very slowly, only logarithmically. And eventually it should hit zero, at which point the discreteness of the energy levels is important, and we believe that the effective theory is just not applicable at that point. So these are three interesting facts that were known in the 1990s. The mean field theory, the conformal behavior, and the zero temperature entropy. My contribution to this subject was first to simplify the model slightly, and second, I was looking for an example of chaos, maximal chaos. Chaos can be quantified using out-of-time order correlators. And chaos is a very intuitive thing, or so it seems, but it's notoriously hard to measure. So chaos is usually described as a butterfly effect, and that appears in at least two places. There was a story by Red Bradbury, and there is also a statement that a flap of butterflies' wings can change the weather. And how do we actually measure that? We need either two copies of the Earth, one with and one without the butterfly. Or related to the other story, we need time traveling. And we need to go back, change something, some initial condition, and observe the difference. And this can be explored quantitatively using out-of-time order correlators. And for theorists, it's fine, but for experimentalists, it's not. Anyway, so chaos is a property of many systems, and usually the disturbances produced by a butterfly or something else grow exponentially, at least in some range of times. And then the growth saturates. There is one example where the growth exponent was known based on Hooft's work on gravitational shock waves in black holes. And that exponent is and it was proved to be maximal by Moldasena, Schenker, and Stanford. And I was actually conjecturing that it's a universality property. I didn't know whether it was maximal or not. And I was looking for a model that would give that. And the SYK model indeed gives that, up to some correction. Yeah, and that correction is important. It was first found in the SYK model by Moldasena, Schenker, and Stanford. Oh, sorry, by Moldasena and Stanford in the paper comments on the SYK model. This is called a Strini correction because in black holes it's related to strains. Now, let me describe some other aspects of this problem that are slightly more advanced. One can write equations of motion using the mean field approximation. These are the Schwinger-Dyson equations. And there is a bare green function, which is just the derivative with respect to tau. And sigma is the self-energy. And now, these equations can be derived from an effective action, and it has some term plus, I don't remember, plus or minus. And I'll write it sloppily. You can read the exact equation in many papers. So there is an effective action that gives the Schwinger-Dyson equation, and it also gives corrections to the mean field in all orders in 1 over n. It's derived using replicas, and it assumes the replica symmetry, and it ignores certain corrections that are proportional to high orders, like 1 over n squared. But those corrections can be included if one goes to the real replica symmetric ansatz. And it may even include everything. It might even be exactly equivalent to the original problem, but we are not sure whether integrals involved in this approximation converge, because near the saddle everything works, but outside it may or may not work. So the G sigma action, the next thing is to look for a soft mode in the G sigma action. And indeed, there is a soft mode that is relevant at low temperature. It's pretty interesting because we can write this function, g of phi1, phi2, using this variable. But we can also write let me call it conformal, G conformal. And phi is a map from the time circle to the unit circle of length 2 pi. And this can be an arbitrary diffeomorphism of a circle, basically. So there is a degeneracy space that is degenerate in the lowest order in 1 over beta, and the correction shows in high order in 1 over beta. And that correction has the form of a short sum. And one can see that everything depends on this effective parameter beta over gamma. And one can write some consequences of this effective action. In particular, there will be contribution to thermodynamics. Let me just write it. So we can just use the saddle point action. It's not really a minimum, it's a saddle point. It's I star. And if we write I star, and it depends on this ratio, as I said. And one can consider also the free energy. Energy and entropy.
But gamma is a new parameter. It's related to J square or what?
Right. Yeah, I forgot to mention. Gamma is alpha s times n.
Alexei, the phi, that's a diffeomorphism of the circle, right? The phi, that's a diffeomorphism of the circle.
Phi is a diffeomorphism of the circle.
It's nothing to do with the other phi, which is 2 pi tau over beta.
Yeah, well, this phi is a map from 0 beta to 0 2 pi. And these are actually circles because we're gluing the ends. And instead of this linear map, we consider a general map. Yeah, that's.
It's also not defined, I believe.
Alpha s is of the order of 1. But in fact, it's of the order of 10 to the minus 2. It's a numerical coefficient that comes up in simulation. So there is this formula for the entropy which goes to 0 at 0 temperature. And first, this formula is not completely accurate. We'll find a correction. And second, there is something that is completely ignored here. If we want to be more accurate connecting the short chain theory to the full theory, we should read something like this. The logarithm of the partition function of the SYK model. It contains this term plus this term, a constant term, plus and that is the partition function of the short chain. This is a large number proportional to n. That is also proportional to n because gamma is proportional to n. But this is some large constant that is ignored in the short chain theory. And when we try to quantize the short chain theory, we'll find that the actual entropy is infinite, and we can subtract infinity and find a finite number, this number. But in reality, that infinity we are subtracting is not really infinity, it's that.
But it looks like this doesn't depend on J, right? J squared doesn't enter. So it
I said J equals 1, so J should be combined with beta.
Okay, sorry.
Yeah.
Sorry, I missed something. So S naught you say come from regulating the short chain theory?
S naught comes from this mean field calculation.
Right.
It comes from here. This term gives you S naught.
So in particular, it's not there in the short chain effective action, right?
S naught is absent from the action, yeah.
Actually, so that I, the action over there. Yeah. So suppose we treat it as a classical action. We are going to derive that equation between sigma and the G.
Yeah.
Right? But now you are saying that this Z SYK is the full quantum partition function.
Yeah. This is a full quantum partition function.
After we do the path integral of this action.
Okay, we can do the path integral of the whole action, but that is hard in principle.
Second? Sorry?
Yeah, in principle. And David Gross and Vladimir Rosenhaus wrote a paper where they compute corrections to all orders, basically, using diagrams. And this is the perturbative expansion that is related to that action. And it's a very hard calculation. And right now I'm talking about an easier calculation. We extract the soft mode action from this effective action, and that soft mode action ignores these two contributions that come from other places. These are not dynamical contributions. They are just constant at low temperature. But the dynamics is here. So
you could say that there is some large ground state degeneracy, and then there's some collective field, which is the Schwarzschild mode, that describes fluctuation about this ground state.
No, this is not correct. This is a very interesting question. It's very confusing when you think about this extensive entropy. You tend to think it's a ground state, but people have calculated the density of states as a function of energy, and in particular, Moldesen and Stanford did it in their paper numerically, but the states are discrete, and there are exponentially many states. Now, first, near the edge of the spectrum, it's the square root law, like random matrices. Then it turns into a certain analytic function that I will describe, and it shoots up because it's exponentially high. This is rho v. And then it comes down, and it's symmetric. Of course, this is not zero of energy. We should put it here. And that point is E naught. And if we subtract E naught, let's ignore this. And let's focus on this part. Then several groups find the density of states here, and there is a paper with 9 authors about random matrices. There is a paper by Stanford and Witten, and also by Bagret, and Kamenev, 2 papers, where they use different approaches to the quantum short chain problem. And the result is that the short chain can be written as an integral of a density of states. It's and here I'm using some notation. E tilde is gamma times E. Beta tilde is beta over gamma. And yeah, this is the most important formula. So it's the sinh of 2 pi times the square root of 2 E tilde. Okay, this is already about the quantum mechanics. It's related to the second question. And Josephine and I try to understand this result from the Hilbert space perspective. And so did other people, and I'll come to that. I guess I'm done with the introduction. Now let me discuss the questions, and I'll talk more about the quantum short chain model. So let's discuss the partial holography. As I said, there is one indication that the model is holographic. It's the conformal function that is described by a propagator in the hyperbolic plane, or in ADS2 in the Lorentzian case. And one can try to generalize it and to think what would happen if we had not the hyperbolic plane, but some other geometry, but some smooth geometry. So if we consider a propagator in asymptotically ADS or asymptotically hyperbolic plane, but some other metric, we can calculate it using the wave equation in the radial coordinate. And by solving the wave equation in the radial coordinate, we're solving an equation with smooth coefficients that analytically depend on the frequency, but there is a well-defined singularity at the origin. And that singularity gives some information about the behavior of the spectral density. For example, one can consider the spectral density A of omega, and it has poles at Matsubara frequencies. This is for fermions. For bosons, it's without 1/2. At Matsubara frequencies, and actually, I should say it's the inverse spectral density. Has poles, but it doesn't have any other singularities. So there is some consequence for the analytic property of the green function, and it would be interesting to explore whether this property holds. I mean, poles only those frequencies and no other singularities. If this property holds, if we introduce some perturbation, say consider the q equals 4 plus q equals 2 Hamiltonian for the SYK. So in perturbation theory, it seems to be true. So next, I want to discuss something related to gravity.
This statement about the spectral function didn't yet use information about the holography, right? So you could have inferred this directly from the model itself.
You can calculate it from the model itself, but another way to do it is to let me argue in physical terms. So let me draw the ADS picture and the Schwarzschild patch. So these hyperbolas are lines at constant distance to the origin, and this is the Schwarzschild time, which in the classical limit can be identified with the physical time, excluding quantum fluctuations. So we are excluding the quantum fluctuations of the gravitational field. The geometry is fixed. However, there are some fluctuating fields in the bulk. And if we want to measure the correlation function at the boundary, we can put the boundary at constant distance. One of this curve will be the boundary. we can think about the correlation function at this curve being a transformed function on a stretch horizon. The stretch horizon is such a curve that is very close to the light cone. So there is some propagation of waves between these two lines, and those propagating waves satisfy the wave equation with well-known analytic properties. The correlation function on the path horizon is like a free fermion or a free boson. And it's transformed by this curved space. And one can find this transformation. And the analytic property I mentioned follows from the fact that the geometry is smooth, including the origin.
What's the dependence of the various parameters of the effective theory on Q?
Oh, it's complex. It's still analytic. Some 10 functions, sometimes gamma functions, but I don't remember.
Let me see if I understand this a bit better. So, is this a statement that if you were computing quasi-normal modes in your 2D black hole, they would just be given by Matsubara frequencies because this is just ADS2?
Yeah.
Okay.
Yeah, right. But this is a calculation, say, for a free fermion. And my reasoning about A of omega is this. We have incoming wave. We observe it somewhere, and it falls back into the black hole. So this line is like the future horizon of a black hole. It falls back into the black hole. And this is quite similar to the following. We have a wave line, a waveguide, and there is some wave going in. There is some filter in here, and we measure it on the other side of the filter. Say we make a small loop, measure the current in this loop, and the wave goes back in. And we're exploring the properties of this filter. And in principle, one can design some very strange filter that that would give non-analytic behavior. Besides the Kramers-Kronig relation, some standard analyticity properties. But a smooth bulk gives nicer analytic properties. Next, let's consider a holographic relation related to the Schwarzschild model. One can argue that the Schwarzschild model is gravitational. It's kind of a representation of gravity. And one reason for that is that formula for the entropy, which follows from the classical configuration of the Schwarzschild mode. One just considers the simplest function, the linear function phi. Phi of tau is linear, and this way one gets this formula. So a classical configuration gives the entropy of a quantum system. This is a characteristic property of gravity. And indeed, one can relate the Schwarzschild model to gravity, which was done by several groups. Maybe I'll explain it here. First, let's draw the Poincare disk with the Poincare metric and draw some curve in that disk and use this curve to describe the function phi of tau. Tau it will be the proper length on that curve. And phi, which is equal to phi of tau, is just the polar angle. Now, it's a hyperbolic plane, and the radial coordinate r. So we can use the radial coordinate and phi coordinate and write the metric. It's phi So curves that are close to r equals 1 have a large denominator, meaning that those curves are long, and they can be arbitrarily long. And the length of the curve is beta. And one can take the limit where this curve is very close to the Poincare circle, this unit circle. Then beta will be large, and one also needs the assumption that this curve does not wiggle too much. And then the result is the extrinsic curvature of that curve is approximately equal to now by the Gauss-Bonnet theorem, because the curvature is constant, it's minus 2. This is equal to A plus 2 pi, which is the area. A is the area inside the curve. And so the short-chain action is minus gamma area minus length plus 2 pi. So this is the action, and where we should use this action with the constraint that the length is fixed. It's equal to beta. And I should use symbol beta here. So there is an action and a constraint. Given that constraint, this is a constant term, and that is obviously a constant term. So the action is just minus gamma times area. And there is a very intuitive picture. It's a balloon in the hyperbolic plane. There is some air inside the balloon which pushes on the walls. And now in this cartoon, gamma is the air pressure. And one can also introduce a variable m, which is the wall tension. And this m has multiple interpretations, which I will list in a moment. And one can write an equation which is equivalent to the Euler-Lagrange equation for this action, and it's k is equal to gamma over m, which is greater than 1, and that is smaller than gamma. So besides the wall tension, there are multiple interpretations of this number. M first, it's a Lagrange multiplier. Second, it's the wall tension and the balloon picture.
So it's a Lagrange multiplier for the length.
For the length. One can also think about this balloon as a particle moving in the hyperbolic plane, and that particle has an imaginary charge, and it's moving in a magnetic field. In our paper with Josephine, we used a different interpretation that turns out to be more helpful. It's a particle with an imaginary spin moving in the curved space. So m is a particle mass, and one can also write m equal to gamma minus E and this E is the energy in the short chain theory. It's this energy, and it can be written as S squared over 2 gamma. Maybe I should say E is E tilde over gamma, which is A squared over 2 gamma, where S is square root of 2 E tilde, that appears in that formula on the top. So S is an important parameter in the problem. It enters the density of states, and it's related to the energy. So there are multiple interpretations. But this is all boundary theory, because although there is some error inside the balloon, the equation of motion is purely one-dimensional. So there is a related problem called Kitaev gravity. This is the bulk integral inside the balloon. And there is also a boundary term, and I don't remember the sign, but I'll copy it from here. Now, when one considers equations of motion, the equation for phi gives the constraint r plus 2 equals 0. So the geometry is rigid. It's the hyperbolic plane. And this term, again, we use the Gauss-Bonnet theorem, and we also use a boundary condition that the dilaton value at the boundary is fixed. This field phi is called a dilaton. This will be minus phi star over 2 pi times area plus 2 pi. And that number may be identified with gamma in the short chain problem. So this was done by several groups, and the papers are in the list. The dilaton problem in the bulk, the Kitaev problem, is equivalent to the short chain problem at the boundary. Now, I'll discuss an indication that the short chain model is indeed a holographic model. There is a paper by Goel, Lam, Turiachi, and Verlinde who construct a non-trivial geometry using massive fields and argue that the Rui-Canadi relation holds. So it's certainly gravity, and there is a formal relation between bulk and boundary, but let me ask this question. Is there life in the bulk? And I'll argue that there is no life in the bulk, at least in this model. And I'll try to fix it, but I cannot. And maybe with your help, we will do it together. So what is the actual question about holography? We would like to have non-trivial bulk dynamics, something non-trivial happening in the bulk. And one way to induce a non-trivial dynamics is to change the J-Kitaev action. This Lagrangian density can be replaced by a different Lagrangian density, including this minus 1 over 4. L dilaton is minus 1 over 4 pi times so there is a linear term in the J-Kitaev theory, and we can add a quadratic term. And we can add higher order terms. In fact, we can consider an arbitrary dilaton potential. What's known about this more general problem classically? The geometry is still rigid. And the situation is somewhat similar to Einstein gravity in 3 dimensions. A 3-dimensional black hole, the BTZ black hole, represents a rigid bulk geometry. There are no gravitational waves in the bulk, but there are some boundary modes. And the same is true for the dilaton theory. The bulk geometry is rigid. It's not necessarily constant curvature. With this correction, it's not constant curvature, but it's rigid. Still, one may argue that there is some life in the bulk in the presence of such a term, because the Gauss-Bonnet theorem does not allow one to integrate out the bulk easily. One can integrate out the bulk, but it's via some non-local argument, solving the differential equations in the bulk. So the question is, can this term appear in the SYK model or in a similar model? In fact, it does appear. And that was the subject of our first paper with Josephine. We did 2 calculations in parallel. We did calculation, everything classical, not including fluctuations. One calculation is in the dilaton theory, including this correction, and we calculated the free energy and some correlation function, some effective action. And we did a similar calculation on the SYK side. There is a correction to the free energy, which I will write down, and there is a correction to the short chain action, and that leads to corrections in the correlation functions, but it's rather subtle. Most of those corrections cancel against other things in the SYK model. It's quite subtle. That was first observed by Moldasena in Stanford, and we did it using a different method, and we confirmed that cancellation. This exact cancellation doesn't occur in the out-of-time order regime, in the chaos regime. There is some cancellation, but not that significant. So it would be nice to include this correction in the dilaton theory and explore its consequences for holography. So the simplest result is a correction to the free energy, and this is free energy beta minus 2. Let me write it. Now, from this expression, you might guess that it's all integer powers. It's not all integer powers. There are some fractional powers related to massive modes, higher modes in the bulk. That is not the short chain. It's beyond the short chain theory. However, these two first terms can be explained more easily. The first term is due to the short chain, and the second term may be related to this thing. And so we can write a dilaton correction. We can write a small correction comparing the second term to the first term. And this is in the short chain theory, but in the dilaton theory, it's the ratio of the alpha term and the linear term. And so if we want to see life in the bulk, we want to study this correction on both sides. As I said, Josephine and I studied those corrections, but there is a difficulty with physical interpretation. Although everything is calculable, the physical interpretation is not the one we want. And it comes down to the question whether the bulk physics is local. In the standard holography story, ADS-CFT, the locality in the bulk was related by Polchinski and others to the dimension gap. So for a theory to have a good local bulk description, we need a few light fields, then there should be a gap, and there may be many very heavy fields. But there should be a gap in dimension spectrum. In other words, there shouldn't be too many fields whose mass is comparable with the curvature. Only a few such fields. In the SYK model, one finds a spectrum of conformal dimensions. It's a discrete spectrum, basically evenly spaced, with some corrections at the low line excitations and high line excitations are all evenly spaced. And this is not a sign of a local theory. It suggests otherwise. Now, what does it mean physically? Suppose we have some dynamics in the bulk that involves many light fields. First, taking those light fields into account will prevent us from having a nice local theory. This is one problem. We have to take infinite series and they may diverge, and if we regularize them, we get something different from ordinary local theories. But the second problem is more physical. I'll use the condensed matter language. Suppose it's some medium with gapless or low-line excitations, and we shake that medium. We just send some gravitational signal. It doesn't have to be a wave. It can be external shaking by introducing some perturbation at the boundary, and the system will react somehow. If there are light modes, they will be excited, and there will be some dissipation associated with that shaking. Now, the dissipation can be quantified in the SYK model, and it's related to chaos. The dissipation can be associated with the correction to the Lyapunov exponent, the exponent that characterized the out-of-time order correlator growth. So let me write down some formula for that. Sorry. So and Mollison and Stanford found this correction, and they found it by solving a so-called ladder kernel. And that was, in fact, my first method to find the first value, but I couldn't do the correction because it's a hard analytic problem. They figured how to do it. So they found the correction by solving the ladder kernel. And the correction... excuse me, I need to grab some of that. This is some strange notation that probably doesn't mean anything to you, except for Q. Q is the parameter of the model. Alpha G is something related to the correction to the Green function, deviation from the conformal regime. And K C of H it's the eigenvalue of Kc it's called the conformal ladder kernel, and it appears in the Euclidean problem. When we calculate the 4-point function, that 4-point function is related to the ladder operator. And Kr of H, it's the eigenvalue of retarded kernel. And the retarded kernel is somewhat like the collision term in the Boltzmann equation. Basically, it's some variant of it. So it's a kinetic coefficient. And one observation pertinent to the SYK model is that this ratio is greater than 1. It actually diverges when Q approaches 2. But in general, it's greater than 1. It turns out that if we go back here, this is Q. And I forgot to put beta here, because it's 1 over beta correction. It's small at low temperatures. So this is the same thing. And so we see that the dissipative effect is greater than the coherent effect. And it means that the bulk dynamics is intrinsically dissipative. And it's unlikely that we can quantize this more general dilaton problem consistently without including other things. And so question number 2. Make it so that or maybe there is a no-go theory. Maybe it's just impossible. But this is reasonably close to a short question, because you see that all these coefficients cancel, and the equation comes down to this ratio between a thermodynamic coefficient and a kinetic coefficient. So it would be nice to look at some variants of the SYK model. There are many such variants. And for example, there is an early model by Sajef and Ye, and there is a more recent model by Sajdev with a complex field, which has some other field, a U1 field besides the short chain. And one may try to look at this model and maybe supersymmetric models, or maybe something else. Okay, then, oh, well, it's already late. But let me just say a few words about the other problem. And it can be, yeah.
So, what's wrong with an intrinsically non-local bulk theory?
Nothing is wrong. However, we live in a world that appears to be local. And there might be some ghosts around, and we may call them from other universes, but so far we haven't seen them. So it's a pretty good illusion of locality, at least. So I won't such a thing.
So how do you get from this observation that you just made to non-locality? What's the connection?
This?
Made some observations about kinetic terms and...
Right. Yeah.
What's the connection?
Okay, this is the physical explanation. Suppose we have some degrees of freedom that resonate at certain frequencies, and we shake the system. If those degrees of freedom are, if they resonate at high frequency and we shake at low frequency, then the dissipation will be low. The fact that the dissipation is high indicates that this shaking resonates with those degrees of freedom, and the frequency is the same as length, so it means that whatever we do at the boundary somehow excites excitations in the bulk. The boundary is a closed system. It doesn't have its own excitations. The short-term may be thought of as an intrinsically boundary theory, but all other stuff has non-local correlation functions. It can be attributed to the bulk. So this shaking or perturbations to the boundary producing dissipative effects means that they resonate with some low frequency modes.
Is that dissipation faster than the time of propagation from the boundary into the black hole?
It's comparable, I think. Well, I'm not sure.
Interpreted as things falling into the black hole in thermal energy?
Well, no. Sorry. Yeah, it's a subtle thing. It's not the usual dissipation as we think in terms of thermalization. This thermalization is already explained by the power law correlation function. It's different. It's a dissipation related to out-of-time order correlators, and this calculation is like chi j of tau chi k and sorry, it should be the real time, the Lorentzian time, rather than the Euclidean time. And this expression is valid when this quantity is much less than 1. Of course, we have to assume that beta is much smaller than n. Then there is a region of times where this quantity is smaller than 1. And then that formula is no longer true. The exponential growth saturates. So this is the exact quantity one computes to extract this kappa, but the bulk interpretation is like this. So that is ADS2, and we can draw a boundary like this. This is the boundary. And we can consider a semi-fill double. And we can produce excitations at time tau, like at time t, kj of t, and k of 0. And this special order indicates that we create some, actually it's written slightly backward. It should be T0, T0 for a better interpretation. It means that we first form a pair of shock waves, so to speak, or a pair of disturbances to the short-chain dynamics. And in the bulk picture, they should be interpreted as shock wave. There is a connection between the shock wave language and the boundary language. The shock waves in anti-de Sitter space can be healed completely by a coordinate transformation. So there will be no shock, but there will be some perturbation to the boundary trajectory. But an alternative language is the language of shocks. So these two shock waves collide, and the correction delta kappa over kappa describes the probability of an incoherent scattering, inelastic scattering. Kappa is due to elastic scattering, and that is inelastic scattering. So my last question was about the quantization of an effective action. Let me just describe the question. We can do the effective action in Euclidean time. It's the G sigma action. And we want to know whether it corresponds to any unitary theory in Lorentzian time. And if it does, we need to find that unitary theory. And this problem has been solved for the short-chain problem. And I hope that I'll have an opportunity, or Josephine will have an opportunity to present our joint work later. It's our work, and there is work of other people who constructed a coarse-grained version of the short-chain model by quantizing the of the SYK model by quantizing the short-chain model. In our language, we have two boundaries that are viewed as particles with some spin and some mass. As I described previously, they propagate through the bulk. And there is a usual TFD, the microscopic TFD. And there is also a TFD that is coarse-grained. And it is described by that pair of particles. We write the wave function for that pair of particles. And the key result we find is that the partition function that is usually written as trace e to the minus beta h has an additional factor p. P is some operator that commutes with the Hamiltonian. And it's somewhat mysterious. It comes out of the calculation, but we don't have a good understanding of its physical meaning. But it's related to the density of states. The sinh is basically that operator P. This operator doesn't appear in the Euclidean problem. It's purely due to the weak rotation. This is a sign that the weak rotation is not a trivial thing, and we should not just assume that everything would work. It may work, but not in an obvious way. And it would be nice to quantize the conformal part of the G sigma action and to combine them with the Schwarzschild. Okay, thank you.
Yeah.
So, in the simplest model of the shady gravity, you have free matter. Do you know what, you included corrections to the dilaton potential. Do you know what happens if you put interaction between the matter and the dilaton, for example?
We didn't do that. Yeah, but it was already complex just with the dilaton and the matter interacting with the Schwarz, with the boundary.
I see. Okay, thank you.
I have a naive question. So, from your free energy, it looks like the asymptotics of the free energy is actually growing faster than that for a quantum mechanical model. There's a t-squared piece, and you said the higher order corrections. Do you know what the asymptotics is at high temperature for the free energy?
Oh, at high temperature, it will be constant at high temperature. Yeah, but that is not the conformal regime.
If there are no further questions, let's have Alexei again.